to let you know, I'm going to for the foundation of mechanics. That mechanics is a major part of physics. That you have seen an aspect of physics. That aspect is mass of time, mass. It is not. We are going one by one. They take on precision. I mean, the fundamental of mechanics. Now, they want meaning when they are in principles and equations of mechanics discussed further in the course of this presentation. So now the concept, we are going to start with space. Now, people take space as a kind of a covering, that is position where you are. Like now you can say, when we say space, some people used to say in the everyday parlor, say give me space. That is shift, that is move further. But in mechanics, space means more than that. Now, the concept of space is associated with the idea of position of a point. Where are you located? Which is described using coordinates. Please, in physics, we have coordinates. When we are talking about coordinates, we have coordinates, two position. We have two position coordinates where we have x and y axis. Then we have three coordinates where we have s, y, z. That is three positions. Is it clear to you? So when you are having, for example, you have a quadratic graph, for example, you are dealing with two positions, s and y axis. Is it clear to you? Because it's a quadratic equation. But when you are dealing with cubic equation, for example, you are dealing with three positions. That is s, y, z. That is s cubed instead of s squared. Is it clear? So now, if you look at the diagram that I have drawn here, if you look at this diagram, you will see that we have s, y, z. We have our traditional sy, which is the x, the y is on the vertical axis, the x is on the vertical axis, is on the horizontal axis, the y is on the vertical axis. Then we have the z, which is cutting across at point 0 of the s and y axis. I believe it is clear. If you are looking at the material, you will see what I'm telling you now. If you have s and y axis, the y is the vertical axis, which is pointing north, while the x is the horizontal axis, that is pointing west. Is it clear to you? Or east. It can be pointing east, it can be pointing west, depending on whether you are dealing with the positive or the negative side. While the y axis that is pointing north can also be pointing south. When it is pointing south, as soon as it crosses the point 0, you are now dealing with the negative part of it. The same thing goes for the s axis. So that is s and y axis, which way we are dealing with two coordinates. But as I've told you, when we are dealing with three coordinates, as we have it in figure 2.11 on the material displayed, then another position need to cross the s and y axis at point 0. That is the z coordinate. Is it clear to everybody? Now the time at which events occur must be recorded if a material is in motion. Is it clear to you? We are dealing with basic mechanics now. So what are we talking about? We hear about rocket launch, like people are launching rockets into space. We hear of falling objects. An orange fall from a tree, an apple fall from a tree. You throw a stone up, it falls down. The time it takes to go up and the time it takes to come down, what we call projectiles in physics, must be recorded. Is it clear to you? I believe people are familiar with projectiles in physics. Now, the concept of mass, you know what is mass? Mass is a measure of the quantity of matter in a substance. Please write down. All these basic concepts need to be defined. Mass is the quantity of matter in a substance. It is measured in kilogram. That is the unit of mass. Mass is different from weight. Mass is weight that is subject to gravity. I believe everybody you are still with me, which means mass is different from weight. You need to understand this fundamental concept because mechanics deal with rigid bodies. Everything mechanics deal with solid bodies, falling objects, time, space, and velocity, acceleration, all sorts of speed, motion, object in motion. That is what we deal with in mechanics. So I've defined mass. That mass is the quantity of matter in a substance. While weight simply is mass subject to gravity. which is F equals ma, mass times acceleration due to gravity. F equals ma is an equation. Equation 1. F, it may not be in the material for this page. We are going to see it later. F, which is force or acceleration due to gravity, equals to ma, mass times acceleration. Is it clear? So that is that about mass. Now enters Newton's law. We are going to deal with Newton's law. That is the laws of motion, which we also have the equations of motion. And in the way that is used to characterize the relationship between the acceleration of a body and the forces that are acting on the body. Finally, a force is something that causes matter to accelerate. I believe you are getting all the definitions. I have defined mass as the quantity of matter in a substance. Is it clear? Now I'm defining force as something that causes matter to accelerate, which means force is mass times acceleration. Is it clear? You can define it simply like that. You can define force simply as mass times acceleration. You don't need to, if you define like that, you are correct. It represents the action of one body on another. Is it clear to you? Now we have different types of forces. We have contact forces, where two bodies touch each other. For example, when you are using what is called what is it called? This what they use to sharpen a cutlass. For example, metals. When you are using all those things, that is a contact force. Then when you put your hand on the surface, you rub your two hands together, contact forces applied. Then in frictional forces, for example, like when you are moving with your, maybe you wear a shoe or you didn't wear a shoe, you have frictional forces in operation. So that is that about force. So I've explained to you the meaning of mass. We've explained space. When I were talking about a particle in space, I was telling you that we have S, Y, Z as coordinates. Is it clear? And I'll tell you that all objects in the space follow this S, Y, Z coordinates, which means they are either in the Y or S or Z direction. Because objects, when they are moving, they have direction. Now that will make me to explain to you the concept of scalar and vector quantity. We still have it in the material later. Is it clear to you? Now, scalar quantities, they are physical quantities that have only mass. Is it clear to you? They have only mass. They don't have direction. Whereas vector quantities, they have both mass and direction. Are you following? Scalar and vector quantities. Scalar quantities, they don't have direction. They only have mass. Why vector quantities, they have both direction and they have mass. I believe people are still following. So that leads us to the fundamental principles. Yes, the fundamental laws of mechanics are the Newton's 3 laws of motion. Everybody should understand this. I'm sure you are doing this course mechanics for the first time at this level, but you would have done it in physics in your secondary school days. You have done mechanics where we are dealing with the laws, Archimedes principles. We are dealing with Newton's law. We are dealing with Copernicus. We are dealing with Michael. All those different concepts by ancient scientists when we are dealing with them. So you would have done all those things. So, but for the purpose of this course we are doing now, I'm going to define Newton's first law. Is it clear to you? The definition is going to be different from what you know before, but the explanation is the same. Now, Newton's first law states that if the resultant force acting on a particle is 0, is it clear to you? What would we mean by resultant force? When a particle is in motion in space, it is not only one force that is acting on that particle. Is it clear to you? For example, when you are in a football field, for example, you watch football matches. Is it clear to you? You see a footballer play a ball far into the sky. There are forces that are acting on that football. Is it clear to you? The forces are many. Now you have force of gravity acting on it. You have other forces that are acting on that ball. The forces that want to take it, that will not make it to come down, then the forces that are trying to bring it down. Is it clear? They are all there. So that's what we mean by resultant force. What I mean by resultant force is that the force that is acting on a particle in space in motion is not one. Is it clear? That is why, for the purpose of this, for this reason, that is why for you to launch a rocket into space, Is it clear to you? For you to launch a rocket into space, for example, then you have to apply what is called escape velocity. Is it clear? That is the velocity that will not make that is more than the force of gravity that is actually on that object. Is it clear? That escape velocity, for example, I'm talking of rocket launch now. We hear people are launching rockets into space. We hear that they are launching satellites into space. You have never been able to ask yourself one day, how do they do this launching? Why is force of gravity not bringing those rockets that they launch into space? Why is gravity not bringing them back? For example, if you throw a stone up, the stone will come back to you immediately. If you throw a ball up, the ball will meet you immediately. But when you launch a rocket, the rocket will not go back to you. That is if the launch is successful. It doesn't come back to you. The rocket is launched and it enters into space. Is it clear to you? It enters into space and it is there doing the work it's supposed to do. For example, we have what is called International Space Station, ISS. All these international space stations, different countries, technological nations like China, like US, like Russia, like Germany, like the UK, they have their rockets. They have their rockets in international space station that are monitoring weather, monitoring sort of things. How do they launch all those things into space? It is because of they use escape velocity, which means the forces that are going to be acting on the object, the force that is taking the rocket up, that is launching into orbit, is more than the force of gravity that is going to bring it down. Is it clear to you? You know this. So that is that. So back to the Newton's first law of motion. If the resultant force acting on the particle is zero, the particle remains at rest. I don't know if you are following. Please write down it. Although you have it in the material, I'm sure the material is shared. I've already shared the material, so you should be able to see it from the material. You should be able to see it from the material. Is it clear to you? Yeah. So if the resultant force acting on the particle is zero, the particle remains at rest. If originally at rest, or we move with constant speed in a straight line, if originally in motion. I'm going to come back to this Newton's first law of motion. Now, the one you know in physics before, if you define it the way you know it in your physics textbook in SS1 or SS2, and you define it this way, it's the same thing. Now, I'm going to define it in a different way, the way you know it. Now, how do you know Newton's first law of motion? It says that everybody remains in a state of rest or in its uniform motion in a straight line unless an external force acts on it. I don't know if it is making meaning to you. These are things you did before your secondary school, but I'm going to come back to it. I believe if I define it in an elementary way, you will understand it better. Now, I said everybody. When I say body, I'm not talking of human being. No, I'm not talking of human being. I'm talking of objects in space. Objects in space. Objects that gravity is acting on. That's what I mean by body. When you throw a football up, when you throw a stone up, when you throw a pebble up, when an aircraft is moving, when a helicopter is moving. All these, those are what I'm talking about. So everybody remains at rest. Is it clear? Everybody remains at rest or in its uniform motion in a straight line unless an external force acts on it. How do I mean? What this first law of motion is telling you, this law has not been distributed up to date. Nobody has been able to come up with a contrary theory as far as Newton's first law is concerned. These laws were propounded over 200 years ago, and they still remain in the same. And these laws have been used to formulate many everyday practical things in science and technology. Like I was talking about rocket launch. I was talking about this thing just now. These are the laws that have been used to create all those hardwares, to create rockets, to create vehicles, to create trains, all the movie objects that we enjoy today in our modern life. All these laws were used. But for now, I'm talking about Newton's first law. Now, I've said that everybody remains in a state of rest or in its uniform motion in a straight line unless an external force act on it. So I'm trying to explain to you that if you keep an object, for example, look at your phone. Just keep that your phone somewhere and travel for 2 years. Keep your phone somewhere in your room and travel for 2 years. If there's no external force acting on that phone, the phone will remain in that place. I believe you know this is correct. Or keep any other object. Maybe keep your electric cooker, or put it on top of a wardrobe. and travel outside Nigeria for 2 years. Go and do your masters abroad and come back in 2 years. If nobody touch that, if no external force act on it, will remain like that. It's going to be there like that. That's what we mean by everybody remains at rest. Every object that is at rest will remain at rest, which implies anything you keep in one spot will remain in that spot. If there are no external factors for forces acting on it, that is on one part of the law. Then the second part of this Newton's first law of motion is that everybody in motion will continue in motion forever until an external force also act on it. What do we mean by this? What it means that if you start moving, for example, you start moving, a car start traveling from here. Say, if there was a straight road that leads to eternity, if there's a straight road that leads to eternity, what this first law is telling you is that once you put your vehicle on that road, or you put your motorbike on that road, or for example, let's use a train track. A train start traveling on a track. What this Newton's first law of motion is telling you is that train will never stop. Is it clear to you? It will travel forever. But we know in everyday life that when you are traveling from here, for example, you are in Lagos, you are traveling to Abeokuta, for example, when you get to a checkpoint, you are going to stop your car. It doesn't move forever because why? External forces are acting on that car to stop it, which is your brakes. Is it clear to you? You apply your brakes, so that is when it will stop. If there were no brakes, you have had a brake failure before. You would have had a brake failure when a driver is moving his vehicle somewhere and he applied the brakes refuse to act. You know that the car cannot stop until it hit a building or hit an electric pole. That is when it will stop. That is what this I'm giving you this illustration for you to appreciate Newton's first law and how it is applied in science today. So that is, I've succeeded in explaining Newton's first law to you. I didn't just define it. I explained it with everyday things. I've told you that solid objects will remain at rest forever if there are no external forces acting on them. And I've also told you that moving objects, like a car that is traveling, will continue to travel forever if there are no external factors acting on it. For example, the brakes, or there is no more fuel. Is it clear? So that is what that is what Isaac Newton, an English scientist, proposed. Now I'm going to continue the explanation. I've explained what we mean by resultant forces before, but I still need to explain it here. By resultant forces, one means the sum of the individual forces which act. The resultant is obtained by drawing individual forces end to end in what is known as the vector. Is it clear to you? Now, you would have in physics, you would have done what is called forces of vectors. That is vector forces. You would have done all these forces that make objects to come to rest. When we are talking of polygon law, vector polygon law, we did all these things in physics. You would have done it in physics. Now, if a body is moving in one direction, there are many forces that are going to be acting on that body. Now, if you look at these illustrations there, if you look at the illustration in figure 2.12, you will see that the three forces F1, F2, F3 act on a single particle. Three forces are acting on a single particle. You can see the direction of the forces. They are coming from different directions and they are acting on one single body. You have F1 is force 1, F2 is force 2, F3 is force 3, acting on a single particle. Is it clear to you? Now, we try to bring all the forces together in the second illustration, which is B. You have F1 and F2. We are trying to use them to form a triangle. Now, in C, you have almost a triangle there. Then you have in D a straight line. Is it clear? Yes. So the resultant of a system of forces acting on a particle A, three forces act on a particle B, construction of resultant force in C, and alternative construction showing that the order in which the forces are drawn is immaterial. That is D. So it can come from any direction. The drawing can come from any direction. So it can be coming from this north, can be coming from the northwest, can be the forces they act naturally. You are not in control of them, are in nature. For example, when you throw a particle up, the forces act haphazardly. So that's what we are shown here. Now, I'm still illustrating Newton's first law. Now we have figure 2.13. In figure 2.13, It shows a floating boat. You know what we mean by a floating boat? You know that boats don't move on tar road. Boats are created or made to move on any body of water, whether large body of water or small body of water. Depending on the complexity of the boat, that will determine how far it can go. Is it clear to you? Now, it can be assumed that there are two forces acting on the boat. Are you seeing the boat in figure 2.13? You should be able to see the boat. Now, before I go further, let me let you know that all the resultant forces that are acting on an object must be equal to 0 for the object to be stable in space. Is it clear? All the resultant for all the forces that are acting on a particular object, whether the forces are 3, whether they are 4, whether they are 5, they must be equal to 0. When the forces are equal to 0, that is when the object can be, the object is said to be balanced. The object will be balanced when the forces are equal to 0. So I continue with my explanation. Now go to figure 2.13. There is a boat there. You know that a boat must be on top of water. Now we know in Archimedes' principle, you would have done Archimedes' principle in physics, that when a boat or any object for that matter, even when you are swimming on water, there is a force that is called upthrust. There is a force that is called upthrust. Is it clear to you? You have a force that is called upthrust. That force is what is acting from the water up, while another force is acting on the water down. Your weight will be acting on the force down, while a force called the upthrust will be acting on the boat up. The two forces must balance for the weight for the boat to be able to float in water from the principle of Archimedes. Is it clear to you? We state that objects display their own weight from the fluid from which they flow. You should know this one in physics, Archimedes' principle, or the principle of flotation. Principle of flotation was taken from Archimedes' principle that objects, materials, displaces their own weight from the fluid in which they float. If a material is not able to displace its own weight from the fluid, they will sink. That's why if you throw stone inside the body of water, it will just go down immediately, because the stone is not able to displace its own weight from the fluid in which it flows. So it's going to go down, which means the forces that are acting on the stone and the forces that are coming, the upthrust, are not equal. When they are not equal, then the object will sink. But if the forces that are coming from the base, that is from the water, and the force of the weight of the material that is on top of the water are equal, then they balance out to 0. Then the body will start floating. This is the principle with which bridges were created. Bridges were created based on these principles. Ships, ocean liners, all moving objects in any body of water were created using the principle of Archimedes, or the principle of flotation. I believe this is clear. So I continue the explanation from there. Now, the illustration that is there, the illustration I gave to you is outside the scope of this illustration. So I go back to this illustration in figure 2.13. Now, it shows a floating boat. It can be assumed that there are two forces with boat weight. Is it clear to you? Which is Fg. There is also an upward buoyancy force that is referred to as upthrust, Fb, exerted by the water on the boat. If these two forces are equal and opposite, the resultant of these two forces will be 0, and therefore the boat will remain at rest. It will not move up or down. Is it clear? It will balance out. This thing also happen in, for example, a balloon. You know, balloon that children used to play during Christmas. Now, if you inflate a balloon, it's not only boat we can use to give this illustration. I'm going to give you another illustration outside the material. If you inflate a balloon and you release it, you release the balloon, you see the balloon will start misbehaving, moving haphazardly, but it will get to a point where the balloon will come to rest. At that point, the forces acting on the balloon and the weight of the balloon balance out. Then the balloon will float. The float is always brief. It's going to float briefly, and fall down to the ground. Is it clear to you? So that is another illustration. So the resultant force acting on the particle of figure 2.13 of 2.12, not 2.13 now, 2.12 as shown in all those first illustrations where I gave you F1, F2, F3 is not equal to 0. It doesn't equate to 0. That's what the point we are given here. The resultant force acting on the particle of figure 2.1 is not 0. And in that case, one applies Newton's second law. Now, Newton's first law only make all these things to balance out, only make forces that are acting on the particle to balance out so that they come to rest, they remain at rest, or when they are in motion, they continue to move. Is it clear to you? So that is that. No, we have explained everything about Newton's first law. Now I'm going to explain Newton's second law. Newton's second law to you. Now I have told you that these Newton's laws of motion, first, second, and third, they have revolutionized the aviation industry, the automobile industry, and even everyday life, even space exploration. These laws did really cause a revolution in those field of study. So I've suggested and explained the first law. Now I'm going to explain the second law, Newton's second law of motion to you. Now the Newton's second law of motion goes like this. If the resultant force acting on a particle is not 0, if the resultant force acting on a particle is not 0, the particle will have an acceleration proportional to the magnitude of the resultant force and in the direction of this resultant force. I come again. If the resultant force, by now you know the meaning of resultant force, that is all the forces that are acting on the material, on the body. Let me use body. All the forces acting on the body, the end product of it is resultant force. Now, if, for example, if the forces are acting on the body, for example, you have F1 plus F2, the first force is 5 Newton and the second force is 3 Newton. If the forces are acting in opposite direction, please listen very well. If the forces acting on the body are in opposite direction, you add them. They call it addition of forces. You will have done these things in physics. So if the force acting in the opposite direction is 10 Newton and the force acting in the other direction is 20 Newton, the resultant force is going to be 20 plus 10 Newton, which is 30 Newton. Is it clear to you? But if these forces are acting in the same direction, you are going to subtract. So if you have the two forces are acting in the same direction, you have 20 Newton and 10 Newton. Then you are going to, instead of 30 Newton, you are going to have 20 minus 10 Newton, which is 10 Newton. Is it clear to you? It should be clear to everybody. Now, the illustration of Newton's second law is F equals ma. Newton's second law. F equals ma. Don't forget that we are dealing with mechanics here. Technical mechanics is the topic. And we are going to, but with our time, I'm going to ensure that we finish this first part today. This material displayed, we ensure that we finish it today, so that next time we go higher in our discussion. Yeah. So I'm still explaining Newton's second law. I said Newton's second law mathematically. Newton's second law of motion, F equals ma, where F is the force and m is the mass and a is the acceleration. Is it clear to you? Now the unit of force is in Newton. The unit of force is in Newton. Then mass is in kilogram and acceleration is in meter per second square. Is it clear? So where F is the resultant force, A is the acceleration, and m is the mass of the particle. The units of the force are the Newton. N, capital N, is the unit of force. Newton. That is a honor. They use it. The unit of honor Isaac Newton. That the English scientists that gave us these laws. All these Newton's law of universal gravity. All those laws, we have them in mechanics. We are going to talk about unit law of universal gravity in the course of this our discussion. Is it clear to you? So the unit of force is Newton. Unit of acceleration are meter per second squared, and I'm told that the unit of mass is kilogram, kg. A force of 1 Newton since F equals ma, we give you a mass of 1 kilogram and an acceleration of 1 meter per second square. I don't know if the illustration is clear to you people. A force of 1 Newton, because the unit of force is in Newton. Is it clear to you? Now, in ancient time, they used to give the unit of force as kilogram per meter per second square. Is it clear? Which is the same thing as Newton. In SI units, the same thing as is Newton. So a force of 1 Newton gives a mass of 1 kilogram and an acceleration of 1 meter per second square. That is that. Now we are going to do our illustration. If the water were removed from beneath the boat, I give you an example of a boat in figure 2.13. If the water is removed from beneath the boat, a non-zero resultant force will act, and the boat will accelerate downwards. I don't know if people are listening. If the water is acting on the boat in form of an upthrust, what this material referred to as buoyancy. Now, if that downward force, that upward force is removed, then there will no longer be a resultant force, because we only get a resultant force if there is a force, two forces acting in opposite direction or acting in the same direction. But in this case, the two forces are acting in opposite direction. A force is acting from the water, which is called upthrust or force of buoyancy, and another force is acting from up, which is a force is acting from south up, and a force is acting from north down. They will balance out. They will equate out to be zero. That is what made the boat to be able to be stable, to be at rest. Is it clear? So now, when you drop a material on top of a table, for example, your smartphone, you drop it on top of a table, that material will remain at rest there because two forces are acting on it. The force that is acting from the table that you dropped it, and the weight of the material you dropped on top of the table. As I'm teaching you now, my laptop is on top of a table here. The laptop has not sink. It's still at rest because the laptop itself has a weight, and the table itself is acting on the bottom of the laptop. The same thing, my phone, my second phone is also on top of the table. So all these things are everyday things that when applied, they make us to wonder. So that will now take us to the Newton's third law of motion. We are going to finish this material today, and when we finish it today, we know that when we come back next time, we're going to go to other higher aspect of a mechanics, a technical mechanics. Now, this Newton's third law of motion is very clear to everybody. I don't think there's any student, any science student that has written why, that has done jump, or even though you have not done jump, you have gone to SS2, SS3, SS1, that does not know Newton's law of motion. Is the most common of the laws of motion because it's very easy to memorize. It says that in every action, there is always an equal and opposite reaction. That is Newton's third law of motion. In every action, there is always a corresponding reaction. State it like that, write it down like that. My own definition. In every action, there is always a corresponding and opposite reaction. That is Newton's third law of motion. But in this material, it is stated, it said each force of action has an equal and opposite force of reaction. Very correct. Is it clear to you? So the force with which you throw a ball to hit a wall, it is that same force with which the ball will get back to you. I believe everybody is following. Everybody is understanding what I'm explaining, and I believe my voice is clear enough for people to hear. So I come again with Newton's third law of motion. This is the bit of mechanics. We told this that you can build a structure. So your structure, I'm sure in mechanics, there you must model now. So and Newton's law of motion, I have a cycle of space, time. Now I'm now explaining Newton's law of motion, and I've explained to you that by my own definition, Newton's third law of motion states that in every action, there is always a corresponding and opposite reaction. And I'll give you a typical example. For example, just have a billiard ball. A billiard ball, like when those people that play snooker, you know snooker, people that play snooker, you see that at the beginning of the game, if they want to start, they hit with that billiard stick, they hit the ball with very high force, and you will see that all the billiard balls, all the balls, they scatter. The force with which you hit the ball is the force with which we get back to you. So if you hit a ball against a wall with a force of 10 Newton, it will come back to you with a force of 10 Newton. Is it clear to you? Now somebody will now explain. Now somebody will now say, what if the ball is not an elastic body? If the ball was not a bounce, it cannot come back. For example, you throw a stone against a wall. How will the stone be able to come back to you with that equal force? Now, you are going to illustrate that one by saying the force with which you throw a stone against the wall will determine the damage that will cause to the wall. That is the reaction. Reaction is not just the reaction does not mean that the ball is coming back to you. Is it clear to you? Now, naturally, if you hit a stone against a wall, you know that the stone will not bounce back to you. Is it clear to you? Even though the stone will bounce back to you, it will not hit you. It will not hit you, but it's going to come back. Is it clear to you? But it has exerted an action against the wall, and the wall has exerted a reaction by hitting the stone back. Now, part of the reaction is going to be the damage to the wall. You will see that if the block is not strong, the stone can even bore a hole through the blocks and enter inside the other and pass through the other side. But if you throw the stone lightly, you throw it just small, maybe it's a kid, a boy of 4 years, throw a stone against a wall, the action will be very minimal and the reaction will be very minimal, but they must be equal and opposite. Then compared to a teenager of 16, 17, 20, 18 years, throw a stone, the impact will be more. Is it clear? So action and reaction are equal and opposite. Newton's third law of motion. So we now quickly do the illustration. We quickly do the illustration for you to understand what we are talking about in Newton's third law of motion. Now, we are going to again consider the boat in figure 2.13. The water exerts an upward buoyancy force, also called upthrust force, on the boat, and the boat exerts an equal and opposite force on the water. Is it clear to you? This is illustrated in figure 2.14. You are going to see it. Now, if you are looking at that figure there, you will see that the force of buoyancy is F3. If you are looking at figure 2.14, in page 3, you will see that the force, the upthrust or the buoyancy force is F3, while or FB, you can name it anything. Why there's an equal force that's coming from up, also an FB, a force that is illustrated F subscript B, also coming down. So the upward force and the downward force, they are acting in opposite direction. They must be equal and balance out for the Newton's third law of motion to hold. And I've told you that in everyday life, all these things are useful, are used in everyday things we see. So you see Newton's third law of motion there, that the water exerts a force on the boat, and the boat exerts an equal and opposite force on the water. What does it cause? It makes the boat to remain stable, for it to be stationary at one spot. Yes, now Newton's laws are used in the analysis of most basic problems and in the analysis of the most advanced complex problems. They appear in many, sometimes they appear hidden, but they are always there in problem of mechanics. Is it clear? Now, just look at your everyday machine, like a generator, like all those baby machines you see in factories. Is it clear to you? Now, you would have seen, for example, look at a generator like a grinding engine in a milling mill or in a mill where they do milling of grains. You see a particular, what they call a force that is moving the what is it called, the spokes. Let me call it the spokes.